Jacobi theory. And it's very simple. So you just start from this freedom in Hamiltonian mechanics, which is given by your canonical transformations. And you know that these are generated by some functions. I'm taking this function to be a function of small q and capital Q, the new coordinate. And then you arrive at the following conditions. So first of all, you require that the Hamilton's equations take the same form. And second, this is your transformation, which your, okay. So given the function f, this is how you find the corresponding canonical transformation. So we have seen these conditions many times already. So now the ingenious idea here is really trying to solve these equations of motion identically. And this will be certainly true if you set the new Hamiltonian, if you completely switch off the time evolution in the new coordinates. And so you're setting h prime equal to 0. And then you say, well, this will be generated by some generating function, which I will call S. And so you will see, so we have now S for three quantities. We have for the action, we have for the Hamilton's function, and now we have for this generating function in the Hamilton-Jacobi theory. They are more or less the same thing, but they are slightly understood differently. So S as an action is a functional. S in the Hamilton's function is a function of the boundary data. And as we shall see, this S here is basically the Hamilton's function so once you solve everything, it's the Hamilton's function. Before you solve it, it's not really. All right. So it's the same S. That's why people use the same letter, but there are slight differences in the meaning. So anyway, so if I set h prime equal to 0, I find that my capital Q is a constant and my capital P is a constant. So I solve these two equations. Now I look at the middle one, and so you have P is a constant, beta, and this is equal to ds, which now depends on Q and alpha because I integrated Q to be alpha, and so you just divide by alpha. So now you see that this is an implicit relation between the constant beta, constant alpha, the solution, and time t. So if you can invert this solution, you have found the solution Q as a function of alpha, beta, and t. In other words, you have found the solution in terms of the two integration constants alpha and beta. Right? So you would be done. Of course, you need to know how to find this S, and it's given by the remaining two relations. So if you look at this one here, h prime is equal to 0, which is ds over dt plus the Hamiltonian, the old one. But now the last one tells us, well, whenever I see small p, I have to plug ds over dq. And so that's what I'm doing here. And so in the end, you get this beautiful Hamilton-Jacobi equation, and you completely transferred your mechanical problem from that many ordinary differential equations to one partial differential equation, which is called the Hamilton-Jacobi equation. So now we're interested in the complete integral of this equation, meaning you really are after the solution which depends on these n integration constants. So if I can find a solution which depends on n integration constants, I just differentiate with respect to the constants, set it equal to another constant, and then invert it, and I have the solution. Okay, so that's the idea. Are there any questions to this? So typically you find these n integration constants by separation of variables, but as I said, this is a coordinate dependent thing, and so some coordinates are better than the others, and it may be a real art to find the coordinates where actually the Hamilton-Jacobi equation separates. So let's now demonstrate this very crazy procedure on a simple example, and then today you will demonstrate it on something much more complicated. So I will have a free-fall in homogeneous gravitational field. So your Hamiltonian is one dimension, p squared over 2m. plus the potential, and the potential is minus mgx. So g is the gravitational constant, and x is our unknown. All right, so we want to solve this problem. We want to solve equations of motion using this horrible procedure here. So the first step is to formulate the Hamilton-Jacobi equation and find S, right? Okay, so the Hamilton-Jacobi, okay, 0 is good. So 0 equals to ds over dt, and then plus the Hamiltonian, where whenever I see p, I just write ds over dx. Okay, so it's plus p squared, so it's ds over dx squared, that stands for p squared, 1 over 2m, and then plus v. And that's your Hamilton-Jacobi equation. So now I told you, you can always try separation of variables, but in certain cases, you are guaranteed that the separation will work. And one such case is if your Hamiltonian doesn't depend explicitly on time, you can separate the energy times time. Okay, so in our case, h is not a function of time. And so we can try S, which depends on x and t, to be S0, which depends only on x, minus e times t. Okay, so this have to work. Right? So now this derivative of S with respect to t just gives me minus e. And then this just becomes ds0 over dx. So we have 0 to minus e plus. So now S0 depends only on x. And I differentiate with respect to x, but now it's a normal derivative. It's not a partial derivative anymore. It's just a normal derivative. So it's ds over dx squared 1 over 2m, and then plus v. So this is an easy ordinary differential equation which you can actually solve. So v is linear in x. So from here you find that S0, missing the 0 there, sorry for that, is just e minus v times 2m square root and integral over x. So it's e minus v times 2m square root of that and integral over x. And surprisingly, because v is linear in x, you can actually integrate it. And so what you find is that your full function s, which is this S0, so after you do integration by Maple, for example, if you are lazy like I am, then you find that this is 1 over 3g m squared 2m e minus v 3/2 and then minus et. So this is your S0 after you have done the integration, and then minus et gives me the full S. Very good. So this is typically the most complicated task, right? To find what this S is. But in this simple case of free fall, we could do it explicitly. So we have our S. And you see that S depends on one integration constant, which is the energy, right? So now this is our integration constant. And the procedure to find the solution is, well, in one dimension, we have one integration constant, everything is fine. So the procedure next is differentiate your S with respect to the integration constant and set it equal to another constant. Okay, so we are doing ds over dE, setting it equal to my new integration constant beta. And again, do it explicitly. It doesn't want to go up. So now I have to differentiate, but now with respect to E. And the result is 1 over mg 2m E minus V, and then minus E, minus T. Minus T, so I'm differentiating with respect to E, right? And so this is my implicit solution, how X, which is contained in V, depends on T and two integration constants, beta and T. Okay, so now the last thing what you have to do is that you have to invert for this X, which is contained here. So it'll be like beta plus T times mg square divided by 2m, whatever you have to do. So in the end, if you do this, so inversion, so X is g over 2 T plus beta square minus E over mg. And this is what you would expect, I hope. So this is just a free fall in the gravitational field, behaves like T square. So now you see the meaning of this constant beta is basically just to send an initial time. So if I start, well, probably I have wrong sign, but anyway, so if I set beta equals 0, I'm just starting at T equals 0 here. You see that this crazy procedure actually works, and it gives you whatever you want, but in the it actually gives you a little bit more, because it gives you the result in terms of these integrals of motion, right? And that's also powerful. So we have E explicitly there, and that's a good thing. Are there any questions to this? All right. So now, as I said, in your tutorial today, you will do much more complicated example, and that will be of the Kepler problem. So we'll be solving Kepler problem by using the Hamilton-Jacobi equation. The solution is in Landau, but I'm hoping that you will produce your own solution. So Hamilton-Jacobi theory is actually a very nice limit of Schrödinger equation. So I told you that you shouldn't be going in the direction from classical to quantum, but rather you should be going from quantum to classical. So let's give an example how really the quantum description by the Schrödinger equation translates into mechanical description of the Hamilton-Jacobi equation. So connection to quantum mechanics. Connection So we start from the Schrödinger equation. So we have a mechanical system, but now the quantum mechanical system. So we have I h bar d psi over dt equals to the Hamiltonian acting on psi. That psi is your wave function. But now we know that your Hamiltonian, is given by this. And in the X representation, the operator P is nothing else just than the gradient. So P hat is minus I. Is it minus? Probably I is there as well. Is there? Maybe not. Not in my notes, so let's hope that's correct. Is there an I here? Yes. There's an I. I h bar gradient. Okay. So this will invalidate my calculation. So anyway, so very good. So this is your quantum mechanical description, and then under certain assumptions, this should translate to your normal mechanical description, right? And so the statement is that you will get the normal mechanical description by simply expanding whatever this is into the leading order in h bar. Okay, and this is called geometric optic approximation. Metric optics, or sometimes WKB approximation. And so what you do is that you say, well, my psi is given by some amplitude, and then e to I h bar s x and t. So this is my phase here. And of course, what you want to, well, okay. So now you're asking what equation S will have to satisfy if I do the expansion in small h bar. Okay, so let's do it. So we have I h bar d psi over dt. Right, so if I differentiate with respect to time, I just differentiate the exponent here, and then I get the same psi. And then I have I squared is -1, so it's minus ds over dt times psi. And then you have the Hamiltonian. So now the Hamiltonian, if I have p square, is the, okay, there's an I, so it's minus h square nabla square over 2m minus h square 2m nabla square plus v acting on psi. That's my Hamiltonian acting on psi. So now I have to differentiate twice this thing here. So there'll be terms which contain nabla square acting on s, and there will be terms containing nabla square, nabla s square. All right, so there will be two terms here. It's nabla s square over 2m minus I h bar 2m nabla square on s plus v. That's what is in this bracket. And the whole thing is times psi. So now you see that the first term where you have just nabla s square doesn't contain h bar because it cancelled, but this one is linear in h bar. So far this is exact result. So now what you want to do is that you want to take the limit h bar goes to 0. So the left hand side is fine. So it's minus ds over dt on psi. And then of course this term will disappear in the limit h bar goes to 0. And so you have nabla s square over 2m plus v acting on psi. But now you see that psi is just a spectator here, and I can delete it from both sides. In other words, I can just write this as nabla s square over 2m plus v plus ds over dt equals to 0. So in other words, your s has to satisfy the Hamilton-Jacobi equation for the particle in the potential. Right? This is just p squared over 2m, but I'm plugging for p nabla s. So this is how you go from quantum to classical using this WKB approximation. And I think this is the most beautiful demonstration how you do it. Of course, yeah, you can change your commutators to Poisson brackets and stuff like that. It also is a transition to classical mechanics. But this is like really, I think it's really nice. Questions, comments? If not, let me start a new topic. So it's part E, is it? Maybe. Let me call it hidden symmetries. And integrable systems. And just a warning, of course, you could spend the whole course on this topic. And so I will just basically touch the things, and I will not prove anything. Well, probably not. I will just give you the flavor of what's going on. So let me start from what we discussed yesterday. And so now you are all familiar with the fact that any phase-based function generates the corresponding vector field and generates the corresponding flow in the phase space. Okay, so let me just repeat this. So given a phase-based function, function I, we can find the corresponding Hamiltonian vector, and it's given simply by the Poisson bracket. So this is what I was trying to convince you yesterday, that if I take the Poisson bracket, leave one spot empty, this is my vector field. And of course, the form of this vector field is just di over dpi, d over dqi, minus di over dqi, d over dpi. So this vector field has a direction in the q, well, it's non-trivial in the direction q, but it can also be non-trivial in the direction p here. Okay, so that's my Hamiltonian vector, and then this generates a flow in phase space with time ti. And so I'm just putting this again. So you have PQ, and you simply, this vector field gives you these integral curves, and then the TI simply tells you how you move along these curves in the phase space. Okay, we know everything about this already. So now let me assume that this vector field, or this flow, is a symmetry of our Hamiltonian. Okay, so let this be a symmetry of H. So what it means is that the Poisson bracket of the two quantities, which is dH over dTi, equals to 0. So now the statement is that as I move along this flow, the value of the Hamiltonian, the Hamiltonian doesn't change. We have conserved energy, but okay. The Hamiltonian doesn't change if I move along this. So this is a symmetry of the Hamiltonian. All right. So now a new concept. So this is in the phase space, right? So I have a symmetry of the Hamiltonian, but the symmetry lives in the space of Q's and P's, right? So now the question is, when you talk about standard Noether's theorem in Lagrangian mechanics, you know that you talk about the symmetries of the configuration space, right? You are asking, I have a system, I can rotate it, is it the same? I have a system, I can translate it, is it the same? But rotation and translation and all these things, they don't only depend on the Q direction. They don't mix with the P direction. P direction is not there, right? So the standard Noether's theorem only talks about the symmetries of the configuration space. Here, suddenly, we have a symmetry in the phase space. So we also employ these P directions. Okay, so this is a much more general notion of symmetry than the standard thing which is typically discussed. So such a symmetry, such symmetry, let me just emphasize that, is at level of phase space. So it's more general than typically discussed in Lagrangian mechanics or whatever. All right. So now there is a geometrical map, which is called canonical projection, which exists in the phase space. So the statement is phase space is equipped with canonical projection This is a really nice feature of Hamiltonian mechanics. You don't get it for, okay. So people studied Hamiltonian mechanics and then they developed a notion of symplectic geometry. But the symplectic geometry don't necessarily have this map here. So actually, Hamiltonian mechanics is symplectic geometry plus extra structure. And that extra structure is basically this guy here. So what is this guy here is simply a map, which if I have Q and P, I just kill P, and left is Q. Okay, so this is a map, which, whatever I have, Q and whatever P I have, it just projects down to the configuration space. So you start with a phase space, and then you go back to configuration space. You forget about P. And this exists in any phase space, doesn't exist necessarily in symplectic space. All right, so now you know about all these push forwards and push backs and whatever. So whenever you have some kind of map which works at the level of points, you can also extend it to vectors and you can extend it to other quantities, right? So there is a corresponding map which also maps my vector fields in the phase space to vector fields in the configuration space. This guy is a vector field in the phase space. Now I want to map it to the guy in the configuration space. Okay, so it takes xi. So let me write it again. So pi star xi. Well, let me just write whatever xi was. So di over dpi, d over dqi, minus di over dqi, d over dpi. Okay, so this is what my xi was before I kill the p direction, right? So here, what I'm doing is I'm killing p. So the same thing will happen with this extension of the map. And so you have the direction in q. So this is a q direction, and this is a p direction. I am moving in the direction d over dpi, right? And so what this map does, it simply kills this p direction. So the map kills p direction. So in other words, this pi star of xi is just given by the first term. Let's call it small xi. And it's di over dpi, d over dqi. We kill the second term, we kill the p direction. And that's what canonical projection of the vector field is. So whatever the vector field you have, if you do apply this p star map, just kills this p direction, and that's it. All right. However, these things here are just the components in the q direction. So xi I and d over dqi. So the components xi. So now you may be asking, is this result, is this small xi a vector field on the configuration space or not? Okay, so the question is xi I, well, is xi, small xi, so this is small, is it a vector in configuration space? Well, what does it mean, a vector in configuration space? Well, a vector in the space of q's must depend only on q, right? It cannot have any piece in it. If it has piece in it, it has still some remnants from the phase space, and it's not a vector field on a configuration space. So that means that the components of this, so xi, I, are only functions of q's. So if it is, then this must be true. It cannot depend on p. So cannot depend on p. So now why is this useful or not? So you have this symmetry here, which is in the phase space. You apply this canonical projection, and you end up with some vector di over dpi, d over dqi. So now you look at the components of that vector. Are the components only q dependent? If they are, this is a vector in the configuration space, and you call and then you can classify the symmetries according to this. So xi, I, you have two possibilities. It's a function of q only. Xi I is a function of q only. Then you call the corresponding symmetry. So this is a vector field on configuration space. And you call the corresponding symmetry an isometry. Well, that's one possibility. The other possibility is that xi depends on q and p. But p is an alien for a configuration space, right? There's no p in configuration space. So this is not a vector in the configuration space. Not a vector in configuration space. And consequently, you call the symmetry a hidden or dynamical symmetry. Hidden or dynamical symmetry. Well, what it actually means is that if I look at my configuration space, because there's no remnant of my symmetry in the phase space, it means there's no transformation I can do in the configuration space to find this symmetry, right? Because the symmetry, this field, depends on p, but you don't know anything about p's when you're just translating your system. So that's why this is a very strange symmetry from the configuration space point of view, and it's called hidden or dynamical symmetry. So you have these two types of symmetries. So by the way, if you look at the energy, okay, so the energy is something like p squared over 2m, let's say. Okay. So now this is my I, which is the constant quantity. So now I find the corresponding xi. Okay, so if you find xi, it's just I. Well, so I doesn't depend on q, so the p direction is gone. And then if I had di over dp, it's just p over m, d over dq, and then plus 0, because it doesn't depend on q. So this is what you find for your capital Xi. So now small xi would kill my p direction, but there is no p direction. So this is also equal to small xi, because there is no p direction there. Okay, but now I look at the components of this vector field, and I see this is my components, and they depend on p. In other words, energy is also a hidden dynamical symmetry. So dynamical symmetry. But of course, that makes sense, right? Because you know that the energy is conserved only when you actually look at the time evolution. If I just look at one time in my configuration space, I don't know that the energy is conserved. There is no transformation I can do to get the energy conserved. The conservation of energy is a consequence that Hamiltonian doesn't depend on time, but I don't know that if I fix time and consider my configuration space at one time. So it actually makes perfect sense that this is a dynamical symmetry. All right. So that's a trivial example of dynamical symmetry. Typically, dynamical symmetries are much more involved. And let me give you a beautiful example of a dynamical symmetry which was known to people already in the 18th century. And that's so consider another example. Example of a dynamical symmetry. So consider a Kepler problem, the Kepler problem. Kepler problem. So it's a motion in the spherically symmetric central force, but the central force has actually a very special form. It's k, some constant over r square, and it's in the direction, in the radial direction. All right, so you will analyze this problem in your tutorial today. But what is obvious is that you have just a motion in spherically symmetric potential or whatever. So again, your Hamiltonian will not depend on time, right? So the Hamiltonian is just p squared 2m plus this potential, and so it doesn't depend on time. So we have the following isometries. Okay. We have a dynamical symmetry. Is a typo in my notes. So we have a dynamical symmetry of the energy. So that's certainly true because this doesn't depend on time. We have also some isometries which correspond to the fact that we have spherical symmetric motion. So what is the corresponding conserved quantity if you have spherical symmetry? Huh?
Angular momentum.
Angular momentum, perfect. So we have also the angular momentum, and you can show that the angular momentum actually is an isometry. Okay, so you have three components of the angular momentum which are conserved, and then you have the energy conserved. So now for arbitrary spherically symmetric potential, this is all you have. However, for a special choice of the force, which is precisely this one, you get something more. And that something more is called Laplace-Runge-Lenz vector. So we also have Laplace-Runge-Lenz vector. Three guys. By the way, if you read Feynman's book on gravitation, he also pretends to discover this Laplace-Runge-Lenz vector on his own. I don't know if he really did discover it on his own or whether he knew that it exists and then pretending that he discovered. Anyway, so what this vector is, it's another concept quantity, and it's a vector. So we have actually 3 more concept quantities, A, and it's given by the momentum times the angular momentum minus the mass of the particle which orbits around your sun, and then you have mk and the direction in r. So this is what it is. The statement is this is a concept quantity. You will show that in your tutorial, but it's a very nice geometrical meaning. So if you consider your ellipse, so you have the sun in one of the foci, another one here. So now you consider, let's say I'm here. Okay, so I'm moving in this direction here, like that. So then this would be the direction m, k, r hat, and then p times l is this direction times l. And then if you subtract them, you find that there is a conserved vector A, which points that direction and has some value. So now if you consider the motions at some other place, so then you have mkr at pointing this direction, p times l will also be pointing this direction. This is p times l. And the difference between the two is the vector A. So the vector A again pointing the same direction, and so will here. And so will here. So really you have 3 conserved quantities. There's a miraculous vector A, which somehow stays constant throughout your motion and points always the same direction, has the same magnitude. And it's given by this mkr minus plus p times l. Okay, and so this is, I think, how Feynman derives his Newton's law. He starts, like, I think, from this quantity here, and then he does some magic. All right, so isn't this amazing? So now we have Kepler problem, which is a 3-dimensional motion, but apparently you have 3 conserved quantities here, another one here, which is 4, and then 3 more, which is 7. Okay, that will be too many. So you can show that not all of them are functionally independent. And you can show that actually you have 2 constraints, so that A times L is equal to 0, and then A square equals to M square K square plus 2M E L square. Okay, so there's 2 constraints, and they tell you that not all these conserved quantities are independent. In other words, we have 3 for L, plus 1 for E, plus 3 for A, minus 2 constraints, and that equals to 5 independent integrals of motion. Okay, so now this is great, and you may feel that this is too much, actually. So what I will tell you in a minute is that you don't need typically that many. In fact, if you have a system with n degrees of freedom, then all you need is 3 integrals of motion, n integrals of motion. So we would, in order this to be integrable system, in order we are able to find the solution, we just need 3 integrals of motion. However, we have 5. So whenever you have more than you need, that makes things more integrable than you need, and they are called super integrable. Okay, so need only 3. Need only 3 to make it integrable. I'll make this more precise in a minute. And so everything in addition to that makes it super integrable, if more than super integrable. So now you can show that there cannot be more than 2n minus 1. It's simply impossible to have more than 2n minus 1. So n is 3 in our case, 2n minus 1 is 5. Okay, so 5 is the maximum number for a system with 3 degrees of freedom. So 5 is the maximum, and hence the system is maximally super integrable. Just the terminology, just to make use of these big words, super integrable and maximally super integrable. So really, the Kepler problem, although it's physically very interesting, right? So it's precisely what describes the motion of planets and stuff like that. It's a very, very special system, like extremely special, because it has more than you need. It has actually the maximum possible number of integrals of motion. Are there any questions? Okay, so I don't have much time, but let me just tell you what this integrability means. Okay, and intuitively, what it means is that, well, if you have a system which is integrable, well, you can actually integrate it, right? So by the way, this notion of integrability, as I will present it, is only true for classical systems. So then you probably heard about integrable quantum field theories and whatever. That means something slightly different. So for example, the new notion about quantum field theories is that you look at the S matrix, about the scattering of the things, and if you can decompose the interactions of n particles into just 2 particle interactions, one after another, then you say that your quantum field theory is integrable. So let's say I collide n particles together, and that would be a huge mess, right? But the statement is I can always decompose it into these 2 interact, and then these 2 interact, and then these 2 interact. And if you can do it, and it gives you the same S matrix, then you say this is an integrable quantum field theory. So this is slightly very, very different notion of integrability here. So definition, you say a dynamical system or system with n degrees of freedom. So we have 2n dimensional phase space is completely in the Liouville sense integrable. This is T, although it doesn't look like that. So it's completely Liouville integrable. As a definition, provided it possesses n. I will put global independent concept quantities Fi function of Q and P, and probably using this stupid notation probably not very useful at this point. So this is a concept quantity which is an integral of motion function of Q of P, but it also takes a specific value. My energy is 5 or whatever. So that's small fi. Is that okay? So anyway, so these are the quantities. So in order this to be conserved quantities, they all have to commute with the Hamiltonian, right? So this must be true. It's just stating that these are conserved quantities. But actually, that's not enough. You also have to impose that are in involution. In involution means that if you take Boston bracket of any two of these, then you get 0. So Fi, Fj equal to 0 for any I and j. Okay, so that's a definition. So I'll call a system a completely integrable system if it possesses n. I didn't say what global means. I didn't say what independent means. But we know what conserved quantities are. H and Fi are Boston bracket is equal to 0. That are in involution, meaning that all of them have to actually commute. Boston commute together mutually. They have to commute. All right, so that's a definition. So now this definition better be useful for something. And there's a theorem. It's called Liouville's theorem. And then the statement is that the solution of equations of motion of a completely integrable system can be obtained you know this archaic word by quadrature. And what I mean by that is a finite number of algebraic operations. Finite number of algebraic operations and integrations. In other words, it means that really, if you have such a nice system which admits these n mutually commuting things and are conserved quantities, then you can actually sort of integrate it in a finite number of steps, which is good, right? So you don't want to spend infinite time. Okay. So now the formulation of the theorem is very vague in the sense like I'm not telling you how to actually do it, but the proof actually tells you how to do it. Okay. So this theorem has a constructive proof which explicitly shows how you integrate your system. Okay. So unfortunately, I don't think I will have time to go through the proof, but it bases on doing the right canonical transformation. So basically, you start with your coordinates q and p, right? And then you want to make a canonical transformation so that your new coordinates are the conserved quantities, and then some other quantities. But you can also show that the Hamiltonian is either one of the quantities Fi or actually is a function of Fi quantities. So this is more general. So Hamiltonian is a conserved quantity, and it must be expressible in terms of these Fi's of the other conserved quantities. Typically, F1 is the Hamiltonian, and then it's simple relation here. H is just F1. All right. So you have that. So now, if you look at So I know these guys, so I know the solutions, the Fi are constant. So what about psi's? So psi's derivative, psi I derivative is just given by h psi I. I can calculate this Poisson bracket in terms of the new quantities. And then it's just dh over the psi I, dfi. Okay. But because h, well, is a constant quantity and depends on these fi's, this will be, again, a constant quantity, right? So this is, let's call it omega I, which is a constant because it only depends on these constant quantities fi's, right? In other words, I know that psi dot is a constant. In other words, I can solve psi I is just psi I 0 plus omega t. And I solve the motion. Right? So I know everything about the motion. I know that these guys are constant, and those guys, they just linearly evolve in time. So now, if you've seen an ocean action angle variables, this is basically it. So the statement is you can, for an integrable system, you can always introduce new by canonical transformation, you can always introduce new coordinates such that one of the coordinates is a constant in the motion, and the other variable is an angle. And so what this really describes is basically a motion on a circle. So this is my f, and this is my angle psi. Okay, so you are keeping f constant, and then psi is just an angle, and you're circling around this circle. In other words, you can always map integrable systems to a motion on a circle in one dimension, or in higher dimensions. What is the generalization of a circle? Torus. Exactly. So actually, all integrable systems are, if they don't extend to infinite regions. So for example, I consider a Kepler problem which stays in a finite region of the phase space. Then you can always map that to a motion on a tori. And so one of the things will always remain the same. There is a constant radius of the tori, and that's one variable. And the other variable is just where on the tori I am. I'm circling around in this angle. All right. So this is the idea. So just map from QP to F and psi. Of course, in order you to be able to do this, you need to show that such a canonical transformation exists. In other words, you have to find the corresponding generating function. And when you are trying to find that corresponding generating function, in order this function to be well defined, you somehow have to use this condition that these things have to commute. Okay, and the reason is that if you are in the phase space, so let's say, okay, I'm now skipping many steps, but anyway, so you can go from one point to another point by this direction, or you can go to that some point by another direction. Statement is, in general, you will get something different. Right? If I go this way, I get something else than if I go that way. Provided that this condition is satisfied, actually, this thing will give you the same thing. And so that means that whatever I'm trying to calculate here is actually well defined, and that gives you the right generating function. Questions? So I have only 15 minutes, so let me just explain you what I mean by independent and what I mean by global, because that's the last things which we don't understand. In this definition is what global means and what independent means, and I'll just draw a picture for that. So by the way, I told you that Kepler problem is completely integrable. So let's just concentrate on the quantities E and L, right? So I said we have one E, and we have 3 L's. It's a vector. So now we need 3 integrals of motion which are in involution, meaning all the things commute. Is it actually satisfied by E and L? What do you think? Okay, is there a way around it? So of course I cannot use E and L because I have Lx doesn't commute with Ly, gives you something like Lz, right? Doesn't give you 0, so I cannot choose Lx and y. But what can I choose?
Squared and squared.
Exactly. So that's what you do in quantum mechanics. So for the Kepler problem, you can choose E. You can choose one of the L's, let's say Lz, people choose, and then you can choose L squared. And so if you take these 3 concept quantities, actually they commute, and so they will guarantee that the Kepler problem is integrable. So final remark is what global and independent means. And so we have these concept quantities. Let's say I have F1, and it takes some special value, small f1. Okay. So now if you look at this f1, it's some function of q and p, and this is now suddenly, let's say, equal to 1 or 0 or whatever, right? So what is this type of equation if you think about phase space as normal space? So I have now an equation that is constraining q and p to be equal to something. What is that defined in my phase space? Sorry. Surface, exactly. So a surface. So each integral defines, well, okay. So typically people say surface if it's a 2-dimensional surface. If it's a more-dimensional surface, which however has only one, well, they call it hypersurface, so it doesn't matter. So it defines hypersurface. In phase space. So for example, F1, Q and P equals to 5 is an equation of the hypersurface in this case. But we know that for our special motion, this will be always true, right? So this will be always true. The value of that integral of motion will stay 5 no matter what I do, because it's a constant quantity. That means that the motion is actually confined to the surface, right? I cannot go outside of that surface because I would change the value of this thing. I would not be 5 anymore, but I would be 6. So, and motion is confined to this hypersurface. All right, so picture. I have P, I have Q here. Of course, this is a higher dimensional phase space. So then I have my F1 quantity, F1 equals to F1, and defines one surface here. And no matter what the motion does, but I have to stay in that surface, right? I cannot leave that surface. I will change the value of the integral of motion. But now I have more integrals of motion. So if I have F2, that will correspond to another surface, right? So then I will have a surface like this, and it will intersect my first surface. So this is F2 equals to F2. Again, my motion has to stay in that surface, but so the only possibility is that it actually stays on the intersection, right? Because I have to stay in both surfaces. Okay, so let's call this space M F1 and F2. So the motion has to stay in the intersection in M F1 and F2.
So, is there any relationship between how this hypersurface let's say this,
Intersect, yeah.
how they match within each other respect to the with the Poisson brackets of these quantities?
Okay, so let's leave out the Poisson brackets at this point out, but yeah. So there is this condition of global and independent. Okay, and I have to have n of these things for something. So actually, so if I have, I don't know, 2 degrees of freedom, and I have 2 integrals of motion, then one hypersurface kills one direction, another hypersurface kills another direction, if ideally they actually intersect. And so what you require in order this to be a completely integrable system, require is that the dimension of M F1 to Fn is always n, that each hypersurface actually kills one direction, right? And so then in the end, I have to stay, my motion is constrained to an n-dimensional motion, right? So this is what you require. Of course, this will happen only if the hypersurfaces are never tangent. If they are tangent, if I have one hypersurface like that, another one just touches it, then it will not kill one more direction, right? I'm killing only one direction if I intersect, right? But if I am just tangent, I wouldn't be killing that direction, right? So only if hypersurfaces are never tangent, so that's geometrically, right? So if they are tangent, I'm not killing extra direction, and this guy MF would be n+1, let's say, would have dimension n+1 because I wouldn't kill that extra direction. But if they were tangent, at that point, actually, the integrals of motion are basically the same, right? I have integral of motion this way, but I have integral of motion that way. So at that point, the integral of motion is the same. So actually, that's precisely what it means to be independent or not independent. If they are tangent, they are not independent. So they can never be tangent, and that's what by independence means. Of course, you can use functional independence words and stuff like that, and you can calculate some determinants to realize this. But geometrically, what it means is that the hypersurfaces are never tangent. They always intersect in nice ways. The integrals are always independent. And global.
Sorry.
Yes?
Is it always guaranteed that the surfaces will intersect at all, or even touch?
Okay. If they don't intersect, then you are in trouble as well. Yeah. So what you really require in order this to work is that they do intersect. They are globally defined. They do intersect, and then they foliate your whole phase space, basically. So if you know the thing is defined only here and the other integral is defined only here, they don't help you to integrate.
Is that part of is that implied by the definition of integrable? Or can
That means, yeah, exactly. So global, that's the last requirement, which I am, you are asking about this. Global means they foliate the phase space. So the intersection foliates the phase space. Okay, so that's also part of your requirement. That's part of your definition. So really, if you have one integral defined here in the phase space and one defined here, it doesn't help you. You need to have them to define, all together. They must be behaving nicely. They must be defining these hypersurfaces. These hypersurfaces have to intersect, and so that in the end, whatever the intersection has to have dimension n and has to be globally defined. So your motion is in this space M, f1 to fn, and that has to be half of the dimension of the phase space and has to be sufficiently well defined. And so that's the definition. So now you understand everything about the definition, and the statement is, if this is true, then you can actually integrate the thing. So now I said by finite number of algebraic operations and integrations. So again, I wasn't going through the proof, but this is what you have to do. And if you did go through the proof, you will see that actually it contains one integration and two algebraic operations. So you can actually make this statement, finite number of algebraic operations and integrations, more precise. It's actually one integration and two algebraic operations. Okay, so it's very, very constructive proof. I outline it in the text, so read it if you want. But I think it's a beautiful part of things. So last thing I want to stress is that whatever I was saying about these action angle variables and going from circle to tori, this must be true for any integrable system. So you can map any integrable system to a motion on tori. And if you want to think about it, is that this is something like a harmonic oscillator phase space, right? So if you go to write variables, you just sweep an ellipse or a circle in the phase space. So now if you take harmonic oscillator in several independent directions, in x direction and in y direction, I will have another circle which is orthogonal to this, and then I'll have a motion in that. So that's my torus, or whatever, now T2. So now if you have harmonic oscillator in n directions, you have Tn, and you have this motion, and that motion, whatever. Statement is, this is precisely the topology of any integrable system. So any integrable system can be mapped to that, provided that it stays at a finite region of the phase space. If you consider a hyperbola for a Kepler motion, it goes forever, goes away. So that's not a finite system you want. But if you consider a finite ellipse or whatever, then you are in finite region of the phase space, and it can be mapped to the tori. All right, so read about it if you want. Questions? Yes?
For super integrable, is the dimension thing on the intersection different?
Ah. Very good. So what you can show is that you can have 2n minus 1 functionally independent integrals of motion. So that would actually be reducing to something really, really trivial. However, these integrals of motion cannot commute, right? So what you can show is that you have actually at most n commuting integrals of motion. So I don't think actually in this construction the super integrability really helps you in this construction, what I'm presenting here. But typically the super integrable systems, they have some other nice descriptions. And so you can solve them algebraically without doing actually any integrations and stuff like that. So there are powerful methods which sometimes work for super integrable systems. Doesn't help you with this dual thing, really. I think that's a correct statement. Other questions?
I might have missed this, but so the dimension of that intersection of all of these surfaces needs to be n or
n.
Most n? Exactly n?
Well, here I'm saying, well, I want to forbid this to be more than n, right? So I don't want n plus 1 or n plus 2. I want really going as much as I can by having n hypersurfaces. So I'm killing n dimensions out of the 2n dimensional phase space to get n. Other questions?
Can Can you explain again why that's a torus and not a sphere?
Oh, it can be. Okay, if you it is a sphere. If you can always you can always rescale some directions. And, yeah, so sphere is also a torus.
A sphere is also a torus?
Well, okay, let's leave that. Other questions? So here I really mean probably torus because I want to have independent direction this way and independent direction that way, sort of. But I don't. So certainly for harmonic oscillator, you typically have an ellipse, but I can make it a circle. So now if I have two-dimensional one, I can probably make the radii the same. Yeah.
Is there any notion of approximate integrability?
Exactly. So yes, there is, and that's another beautiful. So this is 19th century, so it's quite old. But now, if you want to go back to the mid 20th century, there is something called Kamp's theorem, Kolmogorov, Arnold, and Moser, somebody like that, theorem, and it tells you that if you perturb your system a little bit, you actually sort of still preserve this torus almost everywhere.
Yeah, I mean, I know that. Well, I'm not talking about a system which is integrable and gets perturbed, but a system which is very complex and exhibits like some kind of near integrability, although it's not close to an exactly solvable system.
I would say that if it exhibits almost integrability, it must be close to some integrable system.
Okay.
Right. So yeah. So people were looking at what happens if you actually go outside of integrability, if you perturb the system a little bit, and this is solved by this theorem, and you can show that many of the features still remain the same, and you can quantify, how much you depart from integrability, and it's of course the beginning of classical chaos or whatever. And so that's already 20th century. Other questions? All right, tutorial complicated problem, Kepler problem by Hamilton-Jacobi theory.